What if the world you see, the solid, dependable reality you navigate every single day, is merely a facade? What if the chair you are sitting on, the air you are breathing, the very atoms that constitute your body are at their core governed by laws so alien, so profoundly counterintuitive that they shatter our most fundamental assumptions about existence itself? We live our lives on the grand classical stage of the universe, a place where things are either here or there, on or off, true or false. But this stage is built upon a hidden ethereal scaffolding, a subatomic realm where such certainties dissolve into a ghostly mist of possibility. This is the quantum world, and it doesn't just operate differently from ours. It operates with a logic that seems torn from a fever dream. It is a world of phantoms and probabilities, where particles can exist in multiple places at once, where they can be both wave and particle simultaneously, and where the simple act of looking at something can fundamentally change what is real. For a century, this chasm between the ghostly quantum and the solid classical has been the deepest, most unsettling mystery in all of science. How does the universe bridge this gap? How does the definite, predictable reality we experience emerge from a foundation of pure, unadulterated weirdness? The answer, we believe, is not found in some mystical force or the power of consciousness, but in a process of sublime elegance, a constant, universal interaction that gently, relentlessly coaxes reality into being. It is a theory known as decoherence, and it is the story of how the universe chooses. To begin this journey, you must first let go of everything you think you know about how things ought to behave. Consider the humble electron a fundamental building block of our world. In your mind, you might picture it as a tiny solid sphere, a minuscule ball bearing zipping around the nucleus of an atom, and sometimes it behaves exactly like that. If you fire it at a screen, it leaves a single tiny dot, a clear and unambiguous mark of its passage, a particle through and through. But this is only one of its identities. When you are not looking, when you are not actively trying to pin it down, the electron undergoes a breathtaking transformation. It ceases to be a single point in space. Instead, it dissolves into a wave of potential, a cloud of probability spreading through its environment like a ripple in a pond. It is no longer just times here, asterisk. It is in a very real sense simultaneously everywhere at times could times be. This is not a metaphor. This is the mathematical and experimental reality of superposition, the foundational principle of the quantum realm. An unobserved particle is not a thing but a smear of possibilities, a ghost existing in a shimmering haze of potential states. It is a whisper of existence, not yet a shout. This dual nature, this impossible marriage of the discrete particle and the diffuse wave, is known as wave-particle duality, and it lies at the very heart of the quantum enigma. Nowhere is this unsettling truth more starkly revealed than in what Richard Feynman called the central mystery of quantum mechanics, the double-slit experiment. The setup is deceptively simple. Imagine a barrier with two thin parallel slits cut into it. On one side, we have a source that can fire single electrons one by one toward the barrier. On the other side, a detector screen records where each electron lands. First, let's close one of the slits and begin firing our electrons. As you would expect, they pass through the open slit and strike the screen behind it, forming a single tight band. Each electron acts like a tiny bullet, leaving a single point of impact. Open the other slit and close the first, and you get another band right where you'd predict. Simple, classical, and reassuring. But now we open both slits. If electrons are truly just tiny particles, the result should be straightforward. Two distinct bands on the screen, a direct composite of the two previous results. But that is not what happens. What appears on the screen instead is something astonishing, something that should be impossible for particles. A complex pattern of many bright and dark stripes emerges, a classic interference pattern. It's the kind of pattern you see when waves of water pass through two openings and their crests and troughs either reinforce or cancel each other out. This pattern proves unequivocally that the single electron traveling on its own did not pass through one slit or the other. It somehow passed through both slits at the same time, asterisk. As a wave of probability, it interfered with itself, cancelling itself out in some locations and strengthening itself in others, before finally choosing a single spot to land on the screen as a particle. It's as if the universe holds its breath, allowing the electron to explore all possible paths simultaneously. Then, at the last possible moment, it exhales, and a single, definite reality clicks into place. This is where the mystery deepens into something truly profound. Baffled by this result, we might decide to cheat. We might place a tiny detector at each slit to find out once and for all which path each electron actually takes. We set up our experiment, turn on our detectors, and begin firing the electrons again. And just like that, the interference pattern vanishes. It's gone. With our detectors in place, we see only two simple bands, exactly what we would expect from tiny bullets. The very act of observing the electrons, of asking the universe, which slit did you go through, forces them to make a choice. The wave of possibility collapses. The ghostly superposition is broken. The electron behaves like a simple, well-behaved particle again. It's as if nature refuses to show you its quantum magic trick. You can either know the path the electron took, in which case it behaves like a particle, or you can see the interference pattern, in which case it behaves like a wave. But you can never ever do both. The universe presents you with a choice. Which reality do you want to measure? Your observation doesn't just record reality, it appears to actively participate in creating it. This measurement problem has haunted physics for a century. What counts as a measurement? Is it a conscious observer, a mechanical detector? Where precisely is the line between the quantum world of overlapping possibilities and the classical world of singular outcomes? It is a question that leads us to the most famous and perhaps most misunderstood thought experiment in the history of science. In 1935, the physicist Erwin Schrödinger, deeply troubled by these implications, devised a scenario to drag this quantum weirdness out of the subatomic shadows and into our familiar macroscopic world. He imagined a cat placed inside a sealed, soundproof box. Alongside the cat is a diabolical device, a tiny amount of radioactive material so small that in the course of an hour there is a precise 50-50 chance that one of its atoms will decay. If an atom decays, it triggers a Geiger counter, which in turn releases a hammer that smashes a vial of poison gas, killing the cat. If no atom decays, the cat remains unharmed. According to the laws of quantum mechanics, until we open the box and make an observation, the radioactive atom is in a superposition. It has both decayed times and times not decayed, but because the fate of the cat is inextricably linked to the state of the atom, the quantum strangeness must infect the entire system. Before the box is opened, the cat itself must also be in a superposition. It is not just that we don't know if the cat is alive or dead. The theory dictates that within the sealed reality of the box, the cat is simultaneously paradoxically 100% alive times and times 100% dead. It exists as a ghostly blend of two contradictory states, a wave function describing a living dead feline. This is of course absurd. We never see cats or any large object in such a state of quantum limbo. The moment we open the box, we will find either a living cat or a dead cat, never a bizarre fusion of the two. Schrödinger's point was not that such a thing could literally happen, but to highlight the philosophical chasm that had opened up. The mathematics that so perfectly described the behavior of atoms seemed to produce nonsensical results when applied to the world we actually live in. The transition from the quantum to the classical was not just a technical detail, it was a crisis. The prevailing explanation at the time, known as the Copenhagen interpretation, essentially advised physicists to stop asking such questions. It posited that the act of measurement by an undefined observer simply caused the wave function to instantaneously and mysteriously collapse into a single definite state. It worked as a practical recipe for calculations, but as a physical explanation it was profoundly unsatisfying. It felt less like a law of nature and more like a surrender, a philosophical sleight of hand that swept the deepest question under the rug. For decades, this was where the story stalled. The quantum world was a realm of pure potential, governed by the elegant Schrödinger equation, where everything evolved as a smooth, deterministic wave of probabilities. Our classical world was a world of definite outcomes of things that happened, and between them was a violent, instantaneous collapse, an ad hoc rule with no physical mechanism to explain it. It was as if there were two sets of laws for the universe, with an arbitrary wall between them. Why does a single atom get to live in a superposition of states for an extended period, while Schrödinger's cat, made of countless trillions of atoms, is never seen in such a state? What is the magic ingredient that comes with size, with complexity, that banishes the ghosts of quantum mechanics? Is it consciousness? As some have speculated, does the universe wait for a mind to observe it before it solidifies into reality? Or is it something far more mundane, yet infinitely more powerful? This is the great divide, the fundamental puzzle that our journey is setting out to solve. We are searching for the bridge between thee and of the quantum world and the awe of ours. The quest for that bridge has led us to a radical and beautiful idea, a concept that doesn't rely on mystical observers or arbitrary collapses. It suggests that the secret to reality's solidity is not found in isolation but in connection. It is a theory called decoherence. It proposes that the transition from quantum to classical is not a sudden, inexplicable event, but a gradual, inevitable process driven by the universe's inherent messiness. Decoherence argues that no quantum system is ever truly isolated. The ghostly superposition of a particle is an incredibly fragile state, a delicate secret whispered between its various potential selves. But the universe is a relentless eavesdropper. Every stray photon of light, every jostling air molecule, every faint gravitational tremor that bumps into our quantum system acts as a tiny act of measurement. Each interaction carries away a minuscule piece of information about the system's state, entangling it with the wider environment. This constant leakage of information, this ceaseless entanglement with the outside world, is what unravels the delicate quantum tapestry. Think of it like a perfect silent chord played in a vacuum. Its pure note, its superposition of harmonies, can sustain itself indefinitely. But now open that vacuum to the air. The vibrations of the chord immediately begin to interact with billions of air molecules, each one carrying away a tiny echo of the sound. The pure note quickly degrades its coherence, lost to the noisy environment, until all that remains is a single fading tone, the classical reality. Decoherence suggests that this is what happens to quantum systems. They are constantly measured by their surroundings, a trillion times a second. The environment itself acts as a vast distributed observer, relentlessly probing the quantum world and forcing it to make choices. It doesn't destroy the other possibilities. It simply makes them impossible for us to ever perceive as their information gets lost in the chaotic noise of the cosmos. A single atom can maintain its superposition because it is relatively isolated. But a cat, a complex warm breathing system of some 10 to the 27 atoms, is in a state of perpetual ferocious interaction with its environment. It cannot keep its quantum secrets for even the most infinitesimal fraction of a second. Its state is instantly broadcast to the universe, and its wave function decoheres into a single stable classical outcome, alive or dead. This, then, is our thesis. The stark wall between the quantum and classical worlds is an illusion. There is no magical collapse, no privileged observer. There is only one set of quantum laws governing everything from a single electron to the largest galaxy. The classical world we perceive is not a different reality. It is an emergent property, the inevitable consequence of quantum mechanics playing out on a massive interconnected scale. It is the universe reading its own story, and in the process, transforming the poetry of potential into the prose of existence. Our journey from this point forward is to uncover the evidence for this profound idea. We will need to venture into the coldest laboratories on Earth, where physicists create pristine quantum states fighting a constant battle against the encroaching tendrils of the environment. We will explore how entanglement, the spooky action at a distance that so troubled Einstein, is not just a curiosity but the very engine of decoherence, the mechanism by which information leaks out into the world. And we will ask an even deeper question. If decoherence explains why we see a single reality, and does it also explain why we see times, this time's particular reality? Could other parallel worlds, the ghost branches of the wave function, still exist, forever hidden from us by this cosmic process of information loss. The mystery of how the quantum becomes the classical is in the end the mystery of how our universe became itself. To find the answer, we must first understand the force that relentlessly tears down the world of possibilities, the constant, chaotic, and creative process of decoherence. What if the world you see, the solid, dependable reality you touch, is just a fraction of the truth? What if beneath this veneer of certainty there exists a hidden realm of shimmering, ghostly potential, a world where every possible outcome of every event exists simultaneously? This isn't a flight of philosophical fancy. It is the breathtaking and deeply unsettling picture painted by our most successful theory of reality, quantum mechanics. And it forces upon us a question that cuts to the very core of our existence. How does a universe of pure possibility give birth to the single concrete world we call home? The answer, we are beginning to realize, is far stranger and more profound than we ever dared to imagine. To find it, we must return to the dawn of the last century, to a time when our understanding of the cosmos was shattered and the giants of physics found themselves staring into an abyss. The old world was a place of comforting certainty. It was a magnificent cosmic clockwork wound by God and set in motion by the unyielding laws of Isaac Newton. Every gear, every planet, every atom followed a perfectly predictable path. If you knew the position and momentum of every particle in the universe, you could in principle calculate the entire future and reconstruct the entire past. This was the dream of Laplace's demon, an imaginary intelligence of infinite computational power for whom the universe held no secrets. There was no room for chance, no place for ambiguity. Reality was a story already written, and we were simply turning the pages. But at the turn of the 20th century, as physicists began to probe the very smallest constituents of matter, they found that the clockwork was broken. The old laws failed spectacularly and completely. They had peered into the atom's heart and found not a miniature solar system of solid, predictable particles, but a maelstrom of inexplicable energies and phantom-like entities. Out of this chaos, a new and radical physics was born. In the vibrant intellectual crucible of Copenhagen, a group of revolutionary thinkers, led by the philosophical patriarch Niels Bohr and his brilliant, restless protege Werner Heisenberg, began to assemble a new set of rules. Their theory, quantum mechanics, was a triumph of human intellect. It could predict the behavior of atoms, the nature of light, and the engine of the stars with staggering precision. It gave us the laser, the transistor, the foundation of our entire digital world. Yet for all its predictive power, the theory presented a vision of reality so bizarre, so contrary to all human intuition that it bordered on madness. At its core was a mathematical entity known as the wave function. This was not a description of a thing, but a description of time's potential asterisk. For a single electron, the wave function isn't a point on a map. It is a ghostly cloud of probability, a haze of existence spreading through space. Within that cloud, the electron is nowhere and everywhere at once. It is in a state of pure, unblemished potential, a condition we call a superposition. It possesses the potential to be here and the potential to be there, and it inhabits all of these possibilities simultaneously. This wasn't just a clever mathematical trick. It had real, observable consequences. The famous double-slit experiment, which would have been discussed in a previous chapter of our journey, proved it beyond all doubt. A single particle left to its own devices behaves like a wave passing through two separate openings at the same time and interfering with itself on the other side. It is as if a ghost walked through two separate doors in a hallway simultaneously. The universe, at this fundamental level, it seemed, was not a collection of definite objects, but a shimmering symphony of overlapping possibilities. Heisenberg then added another layer of profound strangeness with his uncertainty principle. He discovered a fundamental limit, an unbreakable cosmic law that prevents us from ever knowing everything about a particle. The more precisely you measure its position, the less precisely you can know its momentum, and vice versa. It's not a failure of our instruments. It is a built-in feature of reality. The universe, it seems, wears a veil. It refuses to be pinned down to have all its secrets revealed at once. It insists on a fundamental fuzziness, an inherent ambiguity. But here was the great glaring contradiction. We live in a world of definite positions and definite momentums. we do not experience this quantum haze. A thrown baseball does not exist in a superposition of striking the glove and flying into the stands. It follows one and only one path. The cat on your lap is either here or it is not. It is not a fuzzy probability cloud of catness. So, how do you get from one world to the other? How does the ghostly probabilistic quantum realm of potential give rise to the solid, definite classical world of our experience? This chasm between the two realities is the single greatest puzzle in all of science, the measurement problem, and the first attempt at a solution forged by Bohr and Heisenberg in Copenhagen was as brilliant as it was terrifying. They proposed that the shimmering wave function of possibilities persists only as long as the quantum system is left alone unobserved. The moment you try to look at it, the moment you perform a measurement, something dramatic happens. Reality, they argued, is forced to make a choice. This is the concept of wave function collapse. Imagine the universe holding its breath with all possible outcomes held in suspension. Your act of observation of measurement is the signal that forces it to exhale, and in that single instant, the cloud of probability vanishes, collapsing into one single solid definite reality. The electron that was everywhere is suddenly times here asterisk. The particle that was a wave becomes a point. The ghost solidifies into a corpse. The Copenhagen interpretation, as it came to be known, declared that the act of observation doesn't just reveal reality, it plays a role in creating it. The world out there isn't a fixed pre-existing thing. It is a dynamic interplay between the observer and the observed. This was a philosophical earthquake. It demolished the classical idea of an objective reality independent of us. It suggested that we are not passive spectators watching a cosmic play, but active participants whose very gaze helps to write the script. But this revolutionary idea created an even deeper, more troubling set of questions. It solved one problem by creating a Pandora's box of others. Chief among them was the ambiguity of its own central terms. What precisely constitutes a measurement? Where is the magical line where the weird quantum rules stop and the familiar classical rules take over? Is a Geiger counter a purely mechanical device enough to collapse the wave function of a radioactive atom? When it clicks, has it made a measurement, or is the Geiger counter itself a large quantum system composed of trillions of atoms, which itself enters a superposition of having clicked and not clicked? If so, then what collapses the Geiger counter's wave function? Does the collapse only happen when the information reaches a recording device? Or perhaps when the light from the device's display travels across the room? Or does it only finally become real when that light enters the eye of a conscious, living being? This line of questioning leads directly into a philosophical abyss. What or who is an observer? Bohr and his followers were notoriously vague on this point, but some of their successors took the idea to its terrifying logical conclusion. The physicist John Archibald Wheeler and later Eugene Wigner speculated that perhaps consciousness itself was the crucial ingredient. Perhaps the universe of possibility only solidifies into a concrete history when a mind becomes aware of it. This is a staggering thought. It implies that before conscious life evolved, the universe existed only as an uncollapsed branching sea of probabilities. It suggests that your own awareness right now is playing an active role in cementing the reality of the world around you. This idea places humanity not on a lonely rock in a forgotten corner of the cosmos, but at the very center of the story of reality's creation. It is a profoundly unsettling and deeply anthropocentric view, one that made many physicists, including Albert Einstein, deeply uncomfortable. Einstein famously railed against this probabilistic worldview, protesting that God does not play dice. He believed reality was real whether we were looking or not. He once asked a fellow physicist, "Do you really believe the moon is not there when nobody looks?" According to a strict interpretation of the Copenhagen view, the question wasn't entirely absurd. To highlight the sheer paradox of this interpretation, the physicist Erwin Schrödinger, one of the original architects of quantum theory who had grown to despise the Copenhagen view, devised a thought experiment of brilliant, macabre cruelty. It is the most famous thought experiment in history, Schrödinger's cat. Imagine, he said, that we place a cat inside a sealed steel box. Along with the cat, we place a diabolical device, a single radioactive atom so unstable that in the course of 1 hour, there is a perfect 50-50 chance it will decay. This atom is connected to a Geiger counter. If the atom decays, the counter will click. The click will trigger a hammer, which will shatter a vial of poison gas, which will instantly kill the cat. If the atom does not decay, the cat remains alive. We seal the box and wait 1 hour. According to the laws of quantum mechanics, until we intervene, the radioactive atom is not in a definite state of decayed or not decayed. It is in a perfect superposition of times, both times, states, at the same time. But because the atom is linked to the entire system, its quantum uncertainty infects everything else in the box. The Geiger counter is in a superposition of having clicked and not clicked. The hammer is in a superposition of having fallen and not fallen. The poison is in a superposition of being released and not released. And therefore the cat, whose fate is inextricably tied to that single quantum event, must also be in a superposition. It is not alive and it is not dead. According to the unflinching mathematics of the theory, the cat inside the box is somehow incomprehensibly both alive times and times dead simultaneously, a ghostly blend of two mutually exclusive realities. It is only when we, the observer, open the box to check on the cat that the entire system's wave function collapses. In that instant, reality is forced to choose. The atom becomes either decayed or not decayed. The cat becomes either 100% alive or 100% dead. Schrödinger devised this monstrous scenario not as a serious proposition, but as a bitter parody. He was trying to show the absurdity of applying quantum rules to a large-scale, everyday object like a cat. He was asking the Copenhagen school, where does the madness stop? What is the magical force that grants a human observer the power to resolve this ghostly paradox? A power the cat itself apparently lacks. The Hungarian-American physicist Eugene Wigner took this absurdity a step further with his own thought experiment, aptly named Wigner's friend. Imagine the Schrödinger's cat experiment is being conducted inside a sealed laboratory by a scientist, Wigner's friend. After 1 hour, the friend opens the box and observes the cat. Let's say she finds the cat is alive. For the friend inside the lab, the wave function has collapsed. The uncertainty is resolved. The world is definite. But now consider Wigner's perspective. He is standing times outside, times the sealed laboratory. He has no idea what his friend has discovered. From his point of view, as long as the lab is closed, the entire laboratory, the friend, the cat, the box, the atom, is just one enormous quantum system. Therefore, the entire lab must be in a giant superposition. The friend is in a superposition of having seen a live cat and a dead cat. She is in a state of suspended animation, both happy and grieving at the same time. It is only when Wigner opens the laboratory door and asks his friend, "What did you see?" that this grand, macroscopic superposition collapses into a single reality. This thought experiment pushes the measurement problem to its breaking point. It seems to imply that reality is subjective. The friend's reality collapsed at one moment while Wigner's collapsed later. It suggests that a conscious observation is not enough. Perhaps it takes a time-second times conscious observer to collapse the first one. Where does this chain of observers end? Does my reality depend on you observing me and yours on someone else observing you? It leads to a seemingly inescapable solipsism, the idea that only one's own mind is sure to exist. The pioneers of quantum mechanics had given us the most powerful and accurate scientific theory in human history, but in doing so, they had seemingly broken reality itself. They had created a fundamental schism in our understanding of the world. On one side, there was the quantum realm, a ghostly world of probabilities and superpositions governed by the elegant Schrödinger equation. On the other, our classical world of definite outcomes and collapsed certainties. And bridging the two was a vague, ill-defined and almost mystical process called measurement, an act that seemed to require a conscious observer to function. For decades, this was the status quo. The Copenhagen interpretation, for all its philosophical baggage, worked. It allowed physicists to shut up and calculate as the saying went, and their calculations built the modern world. The deep, troubling questions about the nature of reality were often swept under the rug, relegated to late-night discussions in university common rooms. The measurement problem was seen as a philosophical irritation, not a practical scientific one. But the discomfort never truly went away. The idea that our universe requires a conscious audience to snap it into focus felt deeply wrong to many. It seemed like a temporary patch, a placeholder for a deeper truth we had not yet grasped. Surely the universe managed to exist and evolve for billions of years before we arrived to observe it. Surely a star in a distant galaxy is a definite real object, even if no telescope will ever be pointed its way. The puzzle was screaming for a better solution. A new idea was needed, one that could heal the schism between the quantum and classical worlds, an explanation that could build a bridge between the two realms without invoking the magic of a conscious observer. The world was waiting for a theory that could explain how the solid, unwavering reality we know and trust could emerge naturally and inevitably from the strange, ghostly fog of quantum potential. And so the quantum world presented us with an ultimatum, a choice between two seeming impossibilities. On one hand, a universe that only solidifies into existence when a conscious mind decides to look at it. On the other, a ghostly realm of infinite possibilities branching into countless parallel realities with every interaction. For decades, this was the state of play, a philosophical schism at the heart of physics. The Copenhagen interpretation, championed by Niels Bohr, held sway not because it was satisfying, but because it worked. It provided a recipe for calculating outcomes that were stunningly accurate, yet it demanded we abandon the very notion of an objective reality existing independent of our measurements. It told us to calculate, to predict, but never to ask the forbidden question: what is the electron times doing? Times when we are not looking. This gag order on curiosity left a profound sense of unease, a feeling that we had stumbled upon a powerful magical spell without ever understanding the language in which it was written. It was a bargain that one mind, perhaps the greatest of his generation, refused to accept. Albert Einstein, the architect of our modern understanding of gravity and space-time, became the chief dissenter. His objections were not those of a man behind the times. They stemmed from a deep-seated physical intuition, a belief that the universe at its core must be reasonable. He famously quipped that he could not believe God plays dice with the cosmos, but his critique ran far deeper than a simple rejection of randomness. For Einstein, the true poison pill of the Copenhagen view was its reliance on the act of observation as a creator of reality. It seemed to violate a sacred principle, one he called locality. Locality is the simple common-sense idea that an event happening here cannot instantaneously affect an event happening over there. Information, like everything else, has a speed limit, the speed of light. And yet the quantum theory seemed to suggest a strange, ethereal connection that could leap across galaxies in an instant. In 1935, alongside his colleagues Boris Podolsky and Nathan Rosen, Einstein crafted what he believed would be the final fatal blow to this new physics. It wasn't a laboratory experiment, but a thought experiment, a rapier of pure logic known today as the EPR paradox. It was designed to expose what Einstein saw as the absurd, almost mystical consequences of quantum theory. Imagine they proposed a particle that decays into two smaller identical particles shooting off in opposite directions at nearly the speed of light. According to quantum mechanics, certain properties of these particles, like their spin, must be linked. If you were to measure the spin of one particle and find it to be up, you would know instantly and with absolute certainty that its twin, now perhaps light years away, must have a spin of down. They are a matched pair, a set of cosmic twins, forever bound by their shared origin. Herein lies the paradox, the sharp point of Einstein's argument. According to the Copenhagen interpretation, neither particle has a definite spin until it is measured. Each exists in a superposition of both up and down. But the moment you measure particle A on Earth, you don't just collapse its superposition. You seemingly collapse the superposition of particle B, which might now be streaking past the Andromeda galaxy. How could particle B know it was time to become down? Did your measurement here send a signal faster than light across the universe to tell it how to behave? For Einstein, this spooky action at a distance, as he called it, was a clear sign that the theory was incomplete. The only sensible explanation, he argued, was that the particles were never in a superposition at all. They must have had definite predetermined spins from the very moment of their creation. There had to be, in his words, hidden variables, elements of reality that quantum mechanics was simply blind to. The particles were like a pair of gloves separated at birth and mailed to opposite ends of the solar system. The moment you open your box and see a left-handed glove, you instantly know the other box contains a right-handed one. There's no spooky action. The information was there all along, hidden inside the boxes. Niels Bohr's response was swift and profound, but it did little to soothe the philosophical turmoil. Bohr contended that Einstein was making a fundamental mistake by thinking of the two particles as separate entities. Until a measurement is made, they are not two things. They are one, single, indivisible quantum system, a unified whole described by a single wave function, no matter how far apart its components travel. To ask what the spin of particle B was times before times you measured particle A is a meaningless question. It's like asking for the northern coast of a perfect sphere. The concept doesn't apply. Reality, Bohr insisted, is not something you discover. It is something you create through interaction. This clash of titans defined a generation of physics. Was the universe local and sensible with a deeper reality we just couldn't see as Einstein believed? Or was it fundamentally non-local, a bizarrely interconnected web, where space itself was no barrier to an instantaneous connection? As Bohr maintained, for nearly 3 decades the question languished in the realm of metaphysics. There seemed to be no conceivable experiment that could distinguish between Einstein's hidden variables and Bohr's spooky interconnectedness. It was a debate for philosophers, not for working physicists. Then, in 1964, a quiet physicist named John Stuart Bell, working at the CERN laboratory in his spare time, changed everything. Bell was troubled by the vagueness of the debate, by Bohr's almost mystical pronouncements, and the unproven assumptions of Einstein's position. He wanted to drag the argument out of the philosophical clouds and into the harsh, unforgiving light of experimental reality. With breathtaking mathematical ingenuity, he devised a theorem, a testable inequality that could finally put the question to the universe itself. Bell's theorem was a stroke of pure genius. It essentially said this: if Einstein is right, if the universe is local and particles have predetermined properties, hidden variables, then no matter what those hidden properties are, the correlations between measurements on our entangled twin particles must obey a certain statistical limit. You can perform thousands of measurements, changing the angle of your detectors each time, and if you chart the results, they can only be correlated up to a specific mathematically defined amount. However, Bell then calculated what standard quantum mechanics Bohr's theory of a single non-local system would predict for the very same experiment. The result was astonishing. Quantum mechanics predicted that the correlations would be stronger, that they would violate the limit set by local common sense reality. Bell had transformed the EPR paradox from a philosophical debate into a wager with the cosmos. He had found a way to ask the universe a direct yes or no question. Is reality local, or is it spooky? For the first time, we had a way to experimentally prove whether our intuitive classical understanding of the world, or the surreal predictions of quantum theory, held the ultimate truth. The challenge was now for the experimentalists. The theoretical battlefield fell silent, and all eyes turned to the laboratory where physicists began the painstaking work of building machines capable of posing Bell's question. They would need to create pairs of entangled particles, send them flying apart, and measure their properties with exquisite precision over and over, collecting enough data to see which side of Bell's line reality fell on. The first definitive experiments were performed in the early 1980 seconds by a team led by Alain Aspect in Paris. Using photons, particles of light, as their entangled twins, they set up an apparatus of lasers, crystals, and detectors. The setup was a physical manifestation of the EPR thought experiment, but with a crucial twist: the settings on the detectors at either end were changed by a random switch at the last nanosecond, while the photons were already in flight. This closed a critical loophole, ensuring there was no possible way one detector could secretly signal its setting to the other, even at the speed of light. The experiment was asking the question in its purest form. And when the results came in, they were utterly unambiguous. Bell's inequality was violated, and not by a small margin. The universe, it turned out, was even stranger than we had feared. Einstein, the titan of reason, was wrong. Bohr, the purveyor of quantum mystery, was right. Spooky action at a distance was not a bug in the theory. It was a fundamental feature of the universe we inhabit. This discovery sent shockwaves through the foundations of physics. It confirmed that our universe is profoundly non-local. The two entangled photons are not two separate things that happen to be correlated. They are in a very real sense one thing behaving as a single entity even when separated by vast distances. The fabric of reality is woven with these invisible threads connecting points in space-time in ways that defy our classical imagination. Measuring one particle doesn't send a signal to the other. It is more like defining one side of a single unified object. It is an informational handshake that requires no travel time because the information is already shared globally across the entire quantum system. This revelation, as spectacular as it was, brought us full circle back to the central mystery. Bell's theorem proved that the quantum world was undeniably weird, but it still didn't explain the measurement problem itself. It didn't tell us times why times or times how times. The act of measurement forces this strange, ghostly world of superposition and entanglement to vanish, to be replaced by the solid, definite reality we experience every day. But the very strangeness of the result began to plant a new seed of suspicion. The verdict of Bell's experiments made the Copenhagen interpretation's reliance on a conscious observer feel increasingly parochial, even arrogant. If the universe is interconnected by these instantaneous non-local threads, why would the mechanism for resolving its quantum state depend on the neurological activity inside the skull of a particular primate species on a minor planet? In an unremarkable galaxy, the scale of the phenomenon seemed to dwarf the proposed cause. Perhaps physicists had been looking in the wrong place all along. Perhaps the observer was never the important part of the equation. We had been focusing on the eye behind the telescope when we should have been looking at the telescope itself. What, after all times, is times a measurement? It's not a metaphysical act, it's a physical interaction. It is a fragile, isolated quantum system, an electron, a photon being forced to interact with a huge, clumsy, macroscopic device, a detector, a photographic plate, a Geiger counter. This shift in perspective was subtle but revolutionary. The question was no longer, when does a conscious being acquire knowledge? The new, more potent question was, what happens physically when a quantum system becomes entangled, not with a single twin, but with an environment containing billions upon billions of other particles? An act of measurement is not a silent, passive observation. It is a collision. It is an absorption. It is the transfer of quantum information from a soloist performing a delicate, ethereal melody into a roaring orchestra of trillions of chaotic instruments. The observer doesn't collapse the wave function with their mind. The vast, noisy, and complex measuring apparatus does it simply by touching it. The mystery of the collapse, then, might not be a question of consciousness at all, but a question of scale and complexity. It moved the problem out of the realm of philosophy and placed it squarely back into the world of physics, a world of interactions, energy exchange, and information transfer. This emerging viewpoint offered a tantalizing path forward, a way out of the conceptual cul-de-sac. It suggested that there might be no magical collapse at all. Perhaps there is only a process, a physical mechanism by which the ghostly possibilities inherent in a quantum system are gradually washed away, diluted by their entanglement with the surrounding world. The superposition of the electron isn't destroyed. Its information is just leaked, shared, and scrambled across so many particles in the environment, the air molecules, the detector atoms, the photons in the room, that it becomes practically impossible to ever put back together again. The quantum coherence, the pristine state of possibility, is lost to the wider world. From our macroscopic perspective, standing amidst the chaos of that orchestra, the soloist's pure note seems to have vanished, replaced by a single definite sound. We perceive a collapse, a choice being made. But from a God's eye view, no information was truly lost. It was simply spread so thin across the environment as to become irrecoverable. This was the beginning of a new way of thinking, a hypothesis that didn't require new laws of physics or parallel universes or the ghost of consciousness lurking in the machine. It sought an explanation for the emergence of our classical reality from the quantum realm, using the rules of quantum mechanics itself. It proposed that the boundary between the two worlds wasn't a sharp, impenetrable wall, but a gradient, a transition zone governed by interaction and information. The great mystery of the measurement problem might not be a mystery of observation, but a mystery of entanglement on a massive scale. What if the quantum world doesn't truly collapse when we look at it? What if instead it simply decoheres? What if it just gets lost in the crowd, its secrets whispered away into the vast thermal noise of the universe leaving behind the solid, predictable illusion we call reality? And could we, for the first time, actually watch this process of disappearance unfold? We have arrived at the precipice of an immense intellectual chasm, a profound disconnect between the universe we experience and the universe that science tells us truly exists. We've journeyed into the subatomic realm, a ghostly dominion where particles are smeared out waves of pure potential existing in a shimmering haze of every possible state at once. We have confronted the perplexing duality of the double-slit experiment, where a single electron seems to pass through both slits simultaneously, its ghostly selves interfering to create patterns of impossible logic. We've sealed that now infamous cat in its quantum prison, a thought experiment so unsettling it forces us to accept that, until observed, the creature is a phantom blend of life and death, a living paradox suspended between being, non-being. This is the measurement problem, the hard, jagged rock upon which classical intuition shatters. It's the unsettling suspicion that reality itself holds its breath, refusing to commit to a definite state until a conscious mind, until times you, times prize, open the lid and forces its hand. This idea that our gaze is the chisel that sculpts the cosmos from its raw marble of possibility is as unnerving as it is unsatisfying. It feels less like science and more like a strange cosmic solipsism. For nearly a century, this enigma has haunted the heart of physics, a ghost in the magnificent machine of quantum mechanics. It suggested a fundamental schism in nature, one set of rules for the small and unseen, another for the large and familiar, with an arbitrary magical wall between them called measurement. But what if there is no wall? What if the problem isn't a flaw in the physics, but a colossal error in our most basic assumption? What if the act of looking isn't a magical incantation, but merely the final link in a chain of events that has already been unfolding invisibly and inexorably from the first fraction of a nanosecond? The answer, a concept of stunning elegance and profound implication, did not come from adding new Baroque complexities to our equations. It came from realizing we had overlooked the most obvious, ubiquitous and powerful force in the cosmos, the environment itself. We have until now been thinking about our quantum systems, our electron, our radioactive atom, our cat, as if they were perfect celestial solitaries, existing in pristine, hermetically sealed isolation. We imagine them as actors on a dark, empty stage, performing their strange quantum dance entirely for themselves. This is a fiction, a convenient simplification necessary for our thought experiments, but a profound betrayal of reality. There is no truly empty stage in this universe. No system is an island. The cosmos is not a silent, sterile vacuum waiting for us to interact with it. It is a riotously complex, interconnected and noisy place. Every quantum system is perpetually immersed in a vast, chaotic ocean of other particles. It is constantly being jostled, nudged and interrogated by a relentless barrage of environmental influences. Think of a single atom held in superposition. It is not alone. It is being struck by trillions of air molecules every second. It is bathed in the faint ambient glow of thermal radiation, countless photons glancing off it, each one carrying away a tiny fragment of information. It is subtly pulled by the gravitational fields of every other object in the room, on the planet, in the galaxy. Even in the deepest, coldest vacuum of intergalactic space, the faint whisper of the cosmic microwave background radiation, the ancient echo of the Big Bang, ensures that nothing is ever truly left in peace. This is the environment, not just a passive backdrop, but an active, insidious, and inescapable participant in every quantum event. And its constant meddling presence is the key. The secret to why the quantum world appears to collapse into our classical reality lies not in the special act of our observation, but in the relentless universal act of environmental entanglement. This is the revolutionary heart of a theory known as decoherence. It is the story of how the universe all by itself keeps its own records. To grasp the power of this idea, we must revisit entanglement, that spooky action at a distance that so troubled Einstein. We've seen it as a mysterious link between two particles, a shared fate that connects them across any distance. But decoherence theory reveals that entanglement is not some rare exotic phenomenon reserved for carefully prepared laboratory experiments. It is happening constantly everywhere on a scale that beggars belief. Every single interaction between a quantum system and a particle from its environment, a photon, an air molecule, anything at all, creates a new entanglement. It is a form of informational contamination, a whisper of a secret shared. Imagine our electron poised to go through either the left slit or the right slit. In our idealized experiment, it exists in a perfect superposition of left slit and right slit. Its wave function is pure coherent, a perfect harmony of both possibilities. But now let's place it in the real world. As it travels toward the slits, a single photon from a nearby light source happens to bounce off it. In that fleeting, infinitesimal moment, a new entanglement is born. If the electron was on a path toward the left slit, the photon will scatter in a slightly different direction than if the electron was on a path toward the right slit. That single, humble photon now carries a piece of information. Its trajectory has become a record, a tiny flying witness to the electron's position. The electron is no longer truly alone in its superposition. Its state is now inextricably linked, entangled with the state of the photon. The system is no longer just electron, it is now electron and photon. And it's not just one photon, it's another and another. An air molecule drifts by and is nudged differently depending on the electron's path. The system is now electron and photon and air molecule. With every interaction, the initial pristine superposition of the electron bleeds out into the wider world. Its quantum secret is being broadcast, copied, and pasted across countless particles in its environment. Each of these particles becomes a tiny independent record of the electron's would-be position, a distributed network of spies, all reporting on a different aspect of the same event. This process, this relentless informational leakage into the environment, is called decoherence. The word itself is beautifully descriptive. Coherence is what allows the quantum magic to happen. It is the delicate, precise phase relationship between the different parts of the wave function, the part for left slit and the part for right slit. Think of two perfectly synchronized ripples spreading on a still pond. Where their crests meet, they reinforce into a larger wave. Where a crest meets a trough, they cancel out. This is interference, the signature of a coherent quantum state. It's this interference that produces the telltale striped pattern on the screen behind the double slits. The left slit possibility and the right slit possibility are interfering with each other because they are part of the same unified, coherent wave function. But now consider what happens when the environment gets involved. Every time a photon or an air molecule interacts with the electron, it's like a raindrop falling onto the pond. It disrupts the delicate phase relationship. A single interaction is a tiny disruption, but in the real world, these interactions happen with unimaginable speed and frequency. Trillions upon trillions of environmental particles are entangling with the electron every microsecond. It's not a single raindrop, it's a torrential downpour. This chaotic storm of interactions completely scrambles the delicate phase alignment between the left slit and right slit parts of the electron's wave function. The beautiful synchronized symphony of possibilities is drowned out by a deafening roar of cosmic static. The two ripples are no longer able to interfere with one another. They have decohered. The very property that allowed the electron to behave as a wave, to be in two places at once in a meaningful way, has been irrevocably destroyed. The quantum magic has vanished, washed away by the relentless interrogation of the environment. The superposition is still there technically, but it's hidden. It has become a Schrödinger's cat on a cosmic scale, its quantum state now entangled with the states of quadrillions of environmental particles. a secret so widely distributed that it is effectively lost forever. Here lies the breathtaking solution to the measurement problem. The transition from the quantum "and" to the classical "or" is not an instantaneous magical collapse triggered by a conscious observer. It is a physical, gradual, yet astonishingly rapid process driven by environmental entanglement. As the different components of a superposition like cat is alive and cat is dead interact with their surroundings, they each begin to entangle with the environment in a different way. The live cat is warm. It radiates infrared photons. It breathes jostling air molecules. It has a heartbeat sending tiny seismic vibrations through the floor of the box. Each of these interactions creates a record, an environmental fingerprint of the state cat is alive. The states of countless particles in the box, the air, the straw, the metal walls become correlated with the living cat. Simultaneously, the other branch of the wave function, the state cat is dead, is creating its own entirely different set of environmental records. A dead cat is cold, its temperature matching the room. It does not breathe. Its body is still. The photons and air molecules that interact with it become entangled with the state cat is dead. What we have now are two entirely separate branching chains of entanglement. In one branch, the atom has decayed, the cat is dead, and the surrounding environment carries a trillion-fold record of that death. In the other branch, the atom has not decayed, the cat is alive, and the environment is imprinted with a trillion-fold record of that life. Because these two sets of environmental records are almost perfectly distinct or orthogonal in the language of physics, the two branches of the original superposition can no longer find each other to interfere. They have become deaf to one another. The decoherence process driven by the environment has effectively pruned the wave function, separating the possibilities into non-communicating parallel streams of reality. The quantum cat is alive and cat is dead has become a classical choice. Cat is alive, recorded in one version of the environment, or cat is dead, recorded in a completely different version. There is no collapse. There is only a branching, a splitting of realities driven by physical interaction. So where do we, the observers, fit into this new picture? It turns out we aren't the magicians we thought we were. We are simply the last, largest, and most complex part of the environment. The critical process of decoherence doesn't happen when you decide to open the box. It happened almost instantaneously within fractions of a picosecond of the radioactive atom either decaying or not. The Geiger counter, the air molecules, the photons bouncing around inside the box, these were the true observers. They were the first responders, the ones who entangled with the cat's state and destroyed the coherence between its living and dead possibilities, long before your curiosity ever entered the equation. When you finally open the lid, you are not collapsing the wave function. You are simply allowing your own particles, the photons entering your eyes, the neurons firing in your brain to become entangled with the already decohered system. You are in essence plugging yourself into one of the pre-existing branches. If the photons that reach your retina carry the information signature of a living cat, your brain state becomes part of that vast chain of entanglement. You perceive a live cat because you have now joined the universe where the cat is alive. To you in that branch, the other possibility, the dead cat in its parallel universe of entangled particles, is now completely inaccessible. It has, for all intents and purposes, ceased to exist from your point of view. This is a profound shift in perspective. The observer is demoted from a creator of reality to a mere participant. The mystery of measurement is solved not with mysticism, but with physics. The universe doesn't wait for us. It is constantly observing itself, its myriad parts entangling with each other, forcing choices and forging classical reality from the quantum foam, moment by moment, everywhere at once. The solid, definite world we see around us is the grand outcome of this continuous cosmic scale process of decoherence. We have found a mechanism, a physical process that explains how the ghostly probabilistic world of the quantum gives rise to the concrete certain world of our experience. Decoherence theory is the bridge across that chasm we stood before. It tells us that the superposition of Schrödinger's cat was never a stable state for a macroscopic object. It was a fleeting, impossibly fragile condition doomed to be destroyed by the first stray photon, the first vibrating atom. This is why we never see macroscopic objects in two places at once. They are simply too large, too complex, too hot, and too deeply interconnected with their environment to maintain quantum coherence for any meaningful length of time. They are bleeding information into the universe so rapidly that they are effectively pinned to a single classical reality. A dust mote floating in a sunbeam decoheres in a femtosecond. You decohere in a time so short it makes the Planck time, the fundamental quantum of time itself, look like an eternity. We are classical beings, not because of some special law of nature, but because we are monumental walking catastrophes of information leakage, broadcasting our definite state to the cosmos with every breath and every heartbeat. The quantum world isn't hidden from us. We are simply too entangled with the universe to perceive its true nature directly. We have an answer, and it is more beautiful and intricate than we could have imagined. But in solving one great mystery, decoherence presents us with another, perhaps even more staggering in its implications. It has shown us how the universe elegantly splits into separate, non-interfering branches of reality, each containing one possible outcome. It provides the mathematical framework for this separation, but it remains silent on the ultimate fate of these branches. What happens to the reality you didn't end up in? What became of the universe where the cat died? Does that branch of the wave function simply fade away into computational irrelevance? Or does it too continue to exist just as real as our own, running in parallel forever beyond our reach? By solving the parte measurement problem, have we inadvertently stumbled upon the blueprint for a multiverse, and so we are left suspended, caught between two worlds? One, a realm of pure shimmering potential where a single particle can be a wave of infinite possibilities existing everywhere and nowhere at once. The other, our world, solid, definite, and stubbornly classical. The great unanswered question that has haunted physics for a century is how the universe bridges that chasm. How does the ghost of quantum probability solidify into the unyielding certainty of the reality we touch and feel? The answer, it turns out, was not hiding in some exotic new force of nature, nor did it require the mystical intervention of a conscious observer. The answer was all around us all along. It was in the air you are breathing, the faint warmth of the walls around you, the silent cascade of light from a distant star. The universe, it seems, can't keep a secret. This process, the constant, relentless betrayal of quantum privacy, is what we call decoherence. It is not a violent act, not a sudden jarring collapse. It is a death by 1,000 cuts, a whisper campaign on a cosmic scale that erodes the delicate architecture of the quantum world until only a classical ruin remains. To understand it, you must first reimagine the world around you. Think of the environment not as a passive stage upon which events unfold, but as an impossibly vast and curious audience, a teeming multitude of spies, each one desperate to know the state of our quantum system. Every single particle in the universe is a potential informant. An unassuming air molecule zipping through the room at hundreds of meters per second is not just an inert bystander. When it collides ever so gently with our quantum object, our cat in its box, our electron in its superposition, that collision is an act of measurement. It's a tiny, fleeting interrogation. The molecule bounces off, and the angle of its recoil, the slight change in its momentum, now carries a piece of information about where our object was at that instant. A single such collision is almost meaningless, but it is never just one. In the space of a single second, that object is bombarded trillions upon trillions of times. Each collision is another question asked, another secret stolen. And it isn't just the air. The very walls of the chamber housing our experiment are radiating heat, emitting a constant, invisible torrent of infrared photons. Each photon that strikes our system and scatters away becomes another messenger carrying a fragment of the truth out into the cosmos. Even the cosmic microwave background radiation, the faint primordial afterglow of the Big Bang, a silent echo from the dawn of time, bathes everything in the universe in a gentle stream of photons. There is no escape. To exist in our universe is to be constantly, relentlessly observed, to be measured by the very fabric of space-time itself. Now consider what this relentless interrogation does to our system's delicate superposition. Imagine our electron is in a superposition of being in two places at once. Let's call them location A and location B. This isn't just a statement of ignorance. The electron's wave function, its very essence, is simultaneously present at both A and B. The two states are coherent, meaning they can interfere with each other, creating the strange and beautiful wave patterns that are the hallmark of quantum mechanics. They are two voices singing in perfect resonant harmony. But then the environment begins its interrogation. A single photon flies past. If the electron were at location A, the photon would scatter one way. If it were at location B, it would scatter in a completely different way. Because the electron is at both A and B, the photon itself becomes entangled with it. Its own state becomes a superposition, a state of having scattered from A and a state of having scattered from B. The quantum secret is no longer contained within the electron alone. It has leaked. A tiny piece of the quantum coherence, the harmony between A and B, has been imprinted onto this photon, which now speeds away at the speed of light, lost forever to the wider universe. Now multiply that effect by a staggering, incomprehensible number. Another photon hits, another air molecule collides. With every single interaction, a new particle becomes entangled with our electron's location. The information defining the original superposition, the delicate phase relationship, the precise mathematical harmony between the A and B states is smeared out. It is scattered, diluted, and broadcast across an ever-expanding web of countless environmental particles. Think of it like a single drop of vibrantly colored ink, representing the pure quantum state, and the environment is the Pacific Ocean. When that drop falls into the water, the ink is not destroyed. Every single molecule of it still exists, but it is so thoroughly dispersed, so hopelessly entangled with the chaotic churning of the ocean currents that you could never hope to reassemble it. The vibrant, coherent drop is for all practical purposes gone. The interference effects, the quantum magic that relied on the perfect harmony between states A and B, can no longer happen. Why? Because for interference to occur, the paths of A and B must be indistinguishable. But now they are eminently distinguishable. The universe has recorded which path was taken. The photons scattered from path A are on a different trajectory than those from path B. The air molecules that recoiled from A have a different momentum than those that recoiled from B. The two possibilities are now tagged by the environment. They can no longer recombine and interfere. Their coherence has been lost. This process is astonishingly brutally efficient. For a macroscopic object, something even as small as a speck of dust floating in a sunbeam, it is being struck by so many photons and air molecules that its quantum superposition of position would decohere in a time billion of times shorter than it takes for light to cross a single atom. It is for all intents and purposes instantaneous. The quantum world is not robust. It is the most fragile state of existence imaginable. It survives only in the most profound isolation in the shielded, refrigerated stillness of our most advanced laboratories. Out here in the messy, chaotic, warm reality of everyday life, superposition doesn't stand a chance. But decoherence does more than simply destroy quantum interference. It performs a second, even more profound act of creation. It actively selects the properties that are allowed to survive in our classical world. Consider the paradox again. If everything is made of quantum stuff, why don't we see macroscopic objects in superposition? Why don't we see chairs that are simultaneously here and in the next room? Decoherence provides the answer through a concept of stunning elegance. Pointer states. Pointer states are the survivors. They are the specific, stable, classical properties of a system that are robust against the constant surveillance of the environment. They are the states that the environment can measure without disturbing them. Think of an actual pointer on a scientific instrument. Its position is a classical property. You can look at it, shine a light on it, and it stays pointing at the same number. The environment, the light you use to see it, is constantly measuring its position, and this process only reinforces that position. The position of an object is a quintessential pointer state. An object's location is constantly being monitored by photons and particles bouncing off it. This constant measurement doesn't destroy the state of being at a location, it solidifies it. But a superposition of being in two locations at once, that is incredibly fragile. As we've seen, any interaction with the environment immediately entangles the environment with that location information, destroying the delicate coherence between the two possibilities. The environment, through its relentless process of natural selection, effectively filters reality. It allows states that are stable under its watchful eye, the pointer states of position, momentum, and orientation, to persist and become the classical properties we know. All other states, the vast, ghostly, and far more numerous quantum superpositions, are ruthlessly and almost instantly eliminated. Decoherence, then, is the universe's editing process. It dictates the very basis, the fundamental alphabet of our macroscopic reality. The world appears classical to us because the environment is constantly broadcasting information about a specific set of properties, the pointer states, and washing away the information about all other, more exotic quantum alternatives. We are left with a world built only from the most resilient, informationally stable configurations. And this brings us to the most crucial and often misunderstood aspect of the entire theory. For decades, the great mystery was the collapse of the wave function. What was this strange, violent process where a cloud of quantum potential suddenly and inexplicably snapped into a single concrete reality upon measurement? Decoherence shows us there may be no collapse at all. What we perceive as a collapse is an illusion born of our own limited perspective. Let's return to our cat, now entangled with the state of a radioactive atom. Before we open the box, the system is in a superposition: atom decayed cat dead plus atom not decayed cat alive. Now we introduce the environment. Air molecules, infrared photons, even vibrations in the box itself begin to interact with the cat. A photon might bounce off the warm, breathing body of the living cat. Another might bounce off the cold, still body of the dead one. Instantly, the environment itself is pulled into the superposition. The state of the universe bifurcates. One branch now contains a living cat, entangled with a cloud of photons and air molecules that have scattered from its living body. The other branch contains a dead cat, entangled with a times different times cloud of particles that have scattered from its dead body. The two entire branches of reality, cat alive plus environment A and cat dead plus environment B, are now present in the total wave function of the universe. The crucial insight is that these two branches have now decohered from each other. They can no longer interact or interfere. Why? Because their environmental records are completely different. To bring them back into interference, you would need to capture every single particle that interacted with the cat, every photon, every molecule, and reverse its trajectory perfectly, erasing the information that had leaked out. This is not just practically impossible, it is statistically forbidden by the laws of thermodynamics. It is as impossible as unbreaking an egg or unspilling a glass of milk. So, what happens when you, the observer, open the box? You are not some magical agent who collapses the wave function. You are just another large, warm, complex part of the environment. The moment light from inside the box reaches your eyes, the moment your own body heat interacts with the air inside you, become entangled with the system. Your brain, your eyes, your very consciousness become part of the branching process. In one branch of the universal wave function, you see a living cat. The state of your brain now reflects this reality. Your memory records the sight of a living cat. You are now part of the cat alive plus environment A plus observer who sees a live branch. Simultaneously, in the other, now entirely separate and non-interacting branch of the universe, a version of you sees a dead cat. The state of times that times version of your brain reflects times that times reality. Asterisk, that times you is part of the cat dead plus environment B plus observer who sees dead branch. From your perspective, locked within one of these branches, it looks like a random choice was made. The world of possibility seems to have collapsed into a single definite outcome. You only remember seeing one result, but the theory suggests that no collapse ever happened. The other outcome didn't vanish. It simply decohered from your reality. It branched off, carrying a copy of you along with it, to live out its own parallel existence. This is the profound and for some deeply unsettling implication of taking decoherence to its logical conclusion. It leads directly to the many worlds interpretation of quantum mechanics. The universe doesn't choose, it splits. Every quantum interaction, every decay of an atom, every scattering of a photon is constantly, ceaselessly splitting our reality into a near-infinite array of parallel universes, each one as real as our own. Decoherence is the mechanism that shears these worlds apart, making them mutually unobservable and ensuring that from within any single branch, the world appears reassuringly classical, with definite outcomes and reliable laws. It solves the measurement problem by dissolving it. There is no spooky action at a distance, no mysterious collapse. There is only the unitary deterministic evolution of the universal wave function and the inevitable leakage of information that cleaves reality apart. We are not masters of the quantum realm, forcing it to bend to our will through observation. We are passengers adrift on one branch of an ever-expanding cosmic river, forever unaware of the other versions of ourselves floating away on currents we can never cross. The classical world we inhabit is not the fundamental reality. It is an emergent phenomenon, a stable illusion carved out of the infinite quantum plenum by the relentless information scattering process of decoherence. And if this is true, if we live in just one testament of a vast cosmic library of parallel histories, then the questions we must ask ourselves become even more profound. What does this mean for our sense of identity, for the nature of probability and the arrow of time? As we venture deeper, we find that the disappearance of the quantum world doesn't simplify our universe. It reveals a cosmos stranger, vaster and more magnificent than we could have ever dared to imagine. And so the theory stands before us, a breathtaking architecture of logic, an explanation not of collapse but of a quiet, relentless disentanglement from the quantum dream. But a theory, no matter how elegant, remains a ghost until it is confronted by the harsh, unforgiving light of experiment. For decades, the paradox of measurement was a philosophical battlefield, a realm of thought experiments and untestable assertions. We were left to wonder if we could ever truly part the veil to catch the universe in the act of choosing. That era is now over. We have moved from the chalkboard to the laboratory. We have built machines of almost unimaginable precision tools, not just for observing the quantum world, but for challenging it, for pushing it to its very limits, and for watching with our own eyes as its shimmering possibilities bleed away into the stark certainty of our own reality. This is the moment of truth, the point where abstract mathematics must answer to physical proof. The quest begins not by looking at something as impossibly complex as a cat, but by starting small and working our way up, meticulously scaling the ladder from the quantum to the classical. The legendary double-slit experiment, which first revealed the wave-like nature of single particles, became the perfect arena for this confrontation. We already knew that a single electron, an indivisible point of matter, could somehow pass through two slits at once, creating an interference pattern on a screen behind it, a ghost of paths not taken. The question was, how large can you make the electron? How complex can an object be and still perform this quantum magic trick? The answer came from a laboratory in Vienna, in a landmark experiment that would change everything. The team, led by Anton Zeilinger, chose not an electron but a molecule, a beautiful cage-like structure of 60 carbon atoms known as a Buckminster fullerene or buckyball. Think of it, not a fundamental particle but a tiny spherical soccer ball built from 60 distinct atomic nuclei and hundreds of electrons all bound together. It possesses temperature, it can rotate, it can vibrate. By our everyday intuition, this is a solid object, a thing. And yet they aimed to make it behave like a wave. To do this, they had to create a universe of almost perfect isolation. Inside their vacuum chamber, the pressure was dropped to a 10 trillionth of our atmosphere, creating a void emptier than interplanetary space. This was essential to prevent even a single stray air molecule from bumping into the buckyball, and as we now understand, measuring its position. They then heated the buckyballs until they formed a beam, firing them one by one like infinitesimal cannonballs towards a barrier. This barrier was itself a marvel of nanotechnology, a silicon nitride grating with slits carved into it, slits just 50 nanometers wide, 1,000 times thinner than a human hair. If the buckyball were a simple classical object, you would expect to see two distinct bands on the detector screen behind the barrier, corresponding to the two slits it could have passed through. a simple shadow pattern, but that is not what they saw. Slowly, painstakingly, as the individual buckyballs landed on the detector one by one over many hours, an unmistakable pattern began to emerge. It was a pattern of interference. A series of bright and dark fringes, just like the ripples from two stones dropped in a pond. There was no other way to interpret this result. Each 76-atom molecule, this complex piece of matter, had passed through both slits simultaneously. It had been in a superposition of states, its physical presence smeared out into a wave of probability, interfering with itself before landing on the screen as a single definite particle. It was quantum mechanics on a scale never before witnessed, a stunning confirmation that the weirdness was not confined to the subatomic realm, but this was only the first part of their triumph. The true genius of the experiment was what they did next. They had proven that a complex object could maintain its quantum coherence. Now, they would prove how easily that coherence could be destroyed. They began to slowly, deliberately leak a background gas into the pristine vacuum of the chamber. Molecule by molecule, they were polluting the buckyball's perfect isolation. They were introducing an environment. At first, with just a few gas molecules, the interference pattern remained, though perhaps a little less sharp. The buckyballs were still mostly slipping through the quantum net. But as the pressure increased, something dramatic happened. The elegant stripes of the interference pattern began to wash out. The dark fringes became brighter, the bright fringes dimmer. The clear signal of quantum superposition was dissolving into a bland, undifferentiated blur, and when the pressure reached a certain threshold, the interference pattern vanished completely. All that remained were two simple bands, the classical shadow they would have expected all along. The buckyballs were no longer passing through both slits at once. They were behaving like proper, respectable, everyday objects. Why? Because the gas molecules in the chamber were constantly colliding with them. Each collision, no matter how slight, constituted a measurement. Each bump transferred information about the buckyball's position. It's here, or no, it's here, out into the wider environment. The buckyball became entangled with the gas. Its quantum secrets, its delicate superposition of left slit and right slit were no longer its own. That information leaked away, spreading irrecoverably into the thermal chaos of the surrounding gas. The coherence was lost. The system had decohered. Here, in this vacuum chamber, was the entire story of our reality, writ small. We were watching the exact physical mechanism by which the quantum possibilities are pruned down to a single classical actuality. It was not a mystical collapse caused by a conscious observer. It was a physical process as mundane and as certain as friction. It was the universe constantly whispering to itself, sharing information, and in doing so forcing a consensus. Since that pioneering experiment, scientists have pushed the boundary even further, achieving superposition with molecules of thousands of atoms, biological molecules, complex organic dyes. Each time the result is the same. The bigger the object, the more susceptible it is to the environment, and the faster it decoheres into a single stable state. The quantum world doesn't suddenly stop at a certain size. Its effects just become exponentially, unimaginably fragile. This relentless assault by the environment, this process we call decoherence, is not some esoteric laboratory curiosity. It is right now the single greatest challenge standing between humanity and a technological revolution of unparalleled power, the quantum computer. A classical computer, the one you are likely watching this on, stores information in bits, tiny switches that can be either a 0 or a 1. It's a binary black and white world. A quantum computer, however, operates on a profoundly different principle. Its fundamental unit is the qubit, which can be a 0, a 1, or thanks to the magic of superposition, a complex blend of both 0 times and times 1 at the same time. By linking qubits together through entanglement, a quantum computer can explore a vast number of potential solutions to a problem simultaneously. While a classical computer checks pathways one by one, a quantum computer explores a whole landscape of possibilities in a single coherent step. For certain problems like designing new medicines, creating novel materials, or breaking modern encryption, a quantum computer promises an exponential leap in power, a jump as significant as the one from the abacus to the supercomputer. It's a tantalizing prize. But the very source of a qubit's power, its delicate, multifaceted quantum state, is also its Achilles heel. To build a working quantum computer is to declare war on decoherence. It is a heroic, ongoing battle fought in the quietest, coldest, most isolated places on Earth. The qubits themselves are miracles of engineering. They might be single ions trapped and held motionless in a web of electromagnetic fields. Or they might be tiny superconducting circuits cooled to temperatures just a hair's breadth above absolute zero, colder than the deepest voids of space. This extreme cold is necessary to minimize thermal vibrations. The entire apparatus is then encased in layers of heavy shielding, protecting it from stray magnetic fields, from cosmic rays, from the faint radio waves of a nearby cell phone. Engineers are essentially trying to build a tiny bespoke universe for their calculation, one hermetically sealed from the influence of our own, because even the tiniest, most insignificant interaction with the outside world can be catastrophic. A single photon of light bouncing off a qubit is an observation. A subtle vibration traveling through the floor is an observation. A fluctuation in the surrounding magnetic field is an observation. Each one of these events is like a spy from the classical world touching the qubit and asking, "Are you a 0 or a 1?" And the moment that question is asked, the moment that information leaks out, the superposition is destroyed. The qubit decoheres, snapping into a definite 0 or 1. Its rich quantum potential collapses into a mundane classical bit. The calculation is ruined. The magic is gone. The difficulty of this task cannot be overstated. It is like trying to choreograph a ballet for 1,000 ghosts in the middle of a hurricane where the slightest breeze can cause them to vanish. Every improvement in quantum computing is not just a triumph of engineering. It is a victory in our understanding and suppression of decoherence. We are learning with exquisite control how to shield quantum systems, how to detect and correct for the errors that decoherence introduces. In a very real sense, the quest for the quantum computer is a quest to master the very process that creates our reality, to hold it at bay just long enough to perform a computation in that hidden quantum dream space. And with this hard-won practical understanding of decoherence, we can finally return to the scene of the original crime. We can go back to that infamous box and to the poor paradoxical cat trapped within. For 70 years, Schrödinger's thought experiment haunted the heart of physics, a stark and seemingly absurd conclusion that the theory demanded we accept that before the box is opened, the cat is not alive or dead, but exists in a ghostly superposition of both states. It was a paradox that seemed to force a special, almost magical role upon the conscious observer, whose glance was required to collapse the wave function and force the cat into a definite state. Decoherence theory, backed by the evidence from the lab, sweeps this entire philosophical tangle away with breathtaking simplicity and power. Let us rebuild the experiment, but this time let us see it through the eyes of decoherence. Inside the box we have a single radioactive atom. Its decay is a true quantum event governed by probabilistic laws. If it decays, it triggers a Geiger counter. The Geiger counter in turn releases a hammer, which smashes a vial of poison, which then kills the cat. The chain of events is clear, but the Copenhagen interpretation focused only on the beginning of the chain, the atom, and the end of the chain, the conscious observer opening the box. It ignored the vast, complex, and messy world in between. Decoherence tells us to look at the interactions. The moment the radioactive nucleus decays, its emitted particle, an alpha particle say, does not fly through a perfect vacuum. It instantly slams into the trillions of atoms making up the gas inside the Geiger counter. This is the first catastrophic decoherence event. The alpha particle's position becomes entangled with the state of every gas atom it ionizes. Information about the decay has now leaked, spreading like a shockwave. The question of decayed or not decayed is no longer a private quantum secret of the nucleus. It is a public fact recorded in the state of the gas. The superposition of the atom is gone not in minutes, not in seconds, but in femtoseconds, an unimaginably tiny fraction of a moment. But it doesn't stop there. The avalanche of electrons in the Geiger counter creates an electrical pulse. This pulse travels down a wire. The moving electrons in that current are interacting with the billions of atoms in the copper wire, their state becoming entangled with the metal lattice. The information spreads further. The current triggers the mechanism that releases the hammer. The hammer, a macroscopic object, is a chaotic blizzard of around 10 to the 24 atoms, all vibrating and interacting with the air around them. Its state falling or not falling is not a quantum secret. It is broadcast to the trillions of air molecules it collides with on its way down. The information saturates the environment inside the box. Then the hammer smashes the glass vial. The sound waves, the shattering glass, the liquid poison turning to vapor. Each of these is a macroscopic event, a cascade of decoherence with information about the state of the system becoming hopelessly and irrevocably entangled with every particle inside that box. And then there is the cat. A living, breathing, warm-blooded creature. It is not an isolated quantum system. It is a seething, churning engine of 10 to the 26 atoms. Its heart is beating, its blood is flowing, its brain is firing. It is constantly interacting with the air it breathes, the floor it sits on, the thermal radiation it emits. The cat is perhaps the most complex and powerful measuring apparatus imaginable. The very first molecule of poison interacting with a cell in the cat's lungs is enough. That single interaction entangles the fate of the atomic nucleus with the biological state of the cat, which is itself entangled with the entire thermal environment of the box. So you see, the paradox was never a paradox at all. It was a failure of imagination. We failed to appreciate the sheer overwhelming power of the environment. The cat is never in a superposition of alive and dead for any meaningful amount of time. The quantum superposition of the initial atom is almost instantly magnified up the chain of events, but at each step it is brutally suppressed by decoherence. The system is forced to choose decay or no decay at the very first interaction. Long before you or any other conscious observer ever approaches the box, the universe has already made its decision. The cat is either definitively alive, purring in the dark, or it is definitively and tragically dead. There is no in-between. The role of the observer is not to create reality with a glance, but simply to discover the reality that was already there, a reality forged nanoseconds after the experiment began, by the relentless statistical certainty of decoherence. This, then, is the grand revelation. The solid, predictable, classical world that we experience is not a fundamental truth. It is an emergent property. It is the consequence of living in a universe that is noisy, warm, and interconnected. The strange and beautiful laws of quantum mechanics are the bedrock, the true operating system of reality. But we can never perceive that bedrock directly on a large scale because we and everything around us are constantly being battered by a storm of interactions that washes away the quantum weirdness. Every stray photon, every thermal vibration, every jostling air molecule acts as a tiny juror in a constant cosmic poll voting on the state of the universe. And the verdict is always overwhelmingly classical. Decoherence provides the bridge across the chasm that has divided physics for a century. It shows us how our familiar reality, the world of tables you can knock on and chairs you can sit in, arises seamlessly and inevitably from the ghostly probabilistic quantum substrate. It is not a violent collapse, but a gentle, continuous fading of possibilities. The wave function of the universe is not shattered by observation. It is simply read. Its information is copied and scattered so widely and so thoroughly into the environment that its delicate quantum nature is lost, leaving behind only the simple, robust classical fact. We now understand that the classical world is in a sense the most entangled state of all. Your own body is so profoundly entangled with the air, the light, and the ground beneath you that your quantum possibilities were decided long ago. You are anchored in a single stable reality. Decoherence is the cosmic anchor. It is the scaffolding upon which the reliable macroscopic world is built. It resolves the paradoxes it grounds our experience, and it reveals our world not as a departure from the quantum, but as its most complex and magnificent expression. We have found the mechanism, we have seen how the universe chooses, but this profound answer only opens the door to even deeper questions. If our reality is selected from a quantum multiverse of possibilities by environmental information transfer, what then is the ultimate nature of that environment, And what does it mean that we collections of particles forged in that very process can now turn back and comprehend the system that created us? And so we arrive at the threshold. Our journey together began in a place of profound unease, a reality haunted by paradox. We stood before the unsettling enigma of the quantum world, a realm where particles existed in a ghostly fog of all possibilities at once, only to snap into a single concrete state the moment we dared to look. It was a universe that seemed to care about our attention, that waited for a conscious observer to play its cosmic role before the curtain could rise on reality. We confronted the impossible cat trapped between life and death, and watched single electrons behave as if they were everywhere and nowhere, painting patterns of interference that defied all classical intuition. This was the measurement problem, a deep and troubling wound in the otherwise triumphant body of modern physics. It suggested a stark, unbridgeable chasm between the shimmering probabilistic world of the very small and the solid, dependable world we inhabit. For decades, we were left with explanations that felt more like philosophy than physics, invoking the mysterious power of consciousness or postulating sudden, inexplicable collapses of the wave function that followed no known law. The universe, it seemed, was schizophrenic. But the story does not end in this disquieting duality. The resolution, as we have discovered, is not some new exotic force or a concession to the supernatural. It is in fact woven into the very fabric of existence, a process as relentless and fundamental as time itself. The answer was not in isolating the quantum system, but in realizing that nothing is ever truly isolated. This is the profound revelation of decoherence. It is the universe's own secret for keeping its sanity, the grand mechanism that constantly, tirelessly translates the maybe of the quantum into the is of our reality. Decoherence is not an event, it is a continuous unfolding process of entanglement. Think of a single perfect note played by a violin in a vast silent cathedral. For a fleeting moment it is pure, its identity clear and distinct. This is our quantum system in its fragile state of superposition, a coherent wave of possibilities. But now imagine the air molecules in that cathedral, trillions upon trillions of them each, a tiny eager listener. The instant that sound wave propagates, it touches them, it nudges them, transfers a whisper of its energy, gets jostled and deflected in return. The information of that pure note, its phase and amplitude, begins to leak away, shared and smeared across a colossal audience of particles. The note is no longer a solitary entity. Its pristine identity has become entangled with the state of the entire room. To know the note now, you would need to know the exact state of every single molecule it has touched, an impossible task. The information hasn't been destroyed, but it has been scattered, diluted into the vastness of the environment, effectively lost to any local observer. The note has decohered. Its quantum purity has dissolved into the chaotic classical noise of the world. This is what happens to every quantum system, every atom, every electron, every single moment of every single day. They are constantly interacting, bumping and jostling with the outside world. A single photon of cosmic background radiation, a stray air molecule, a subtle vibration in a gravitational field, any of these can act as a spy, an environmental particle that measures the system. This measurement isn't a conscious act. It is a physical interaction, an exchange of information that irrevocably entangles the system with its surroundings. The quantum secret, the delicate superposition of states, is instantly broadcast to the universe. And once that secret is out, it cannot be put back. The Schrödinger's cat is never truly alone in its box. The box itself, the air inside, the radioactive atom, the Geiger counter, the very floor it rests upon, all are part of an immense interconnected environment. Every vibration, every thermal interaction, every stray particle is a question being asked of the cat's state. Is it alive, or is it dead? The question is not asked by you, the human peering in, but by the trillions of particles that make up the box and its local universe. The moment the radioactive atom decays or doesn't, that information begins to hemorrhage into the environment. The entanglement spreads like a shockwave, imprinting the alive or dead state onto the surrounding particles at near light speed. Long before you ever decide to open the lid, the universe is already chosen. The superposition has been shattered not by your gaze but by its own inescapable connection to everything else. The quantum possibilities have been filtered by the environment, which can only sustain one classical outcome. The alive cat and the dead cat branches of the wave function rapidly diverge, no longer able to interfere with each other. They have become separate, parallel realities, and we, being part of this vast environment, are inexorably carried down just one of those paths. This is a tectonic shift in our understanding of ourselves and our place in the cosmos. The observer, the conscious being who haunted the Copenhagen interpretation, is dethroned. We are not the linchpin holding reality together. We are not performing a magical act of creation every time we look at the world. We are simply late to the party. The universe doesn't wait for us. The classical world we perceive is not something we conjure into being. It is the inevitable emergent consequence of quantum mechanics playing out on a macroscopic scale. It is the universe constantly measuring itself. We are not the audience of the cosmic play. We are part of the scenery, the stage, and the cast all at once. Reality is the consensus reached by an uncountable number of microscopic interactions, a grand ongoing negotiation between all the particles in existence. The classical world is robust, stable, and predictable for one simple reason. It is the reality that has been massively, redundantly, and continuously recorded in the environment. A chair is solid and in one place because every particle in it and around it agrees on its location and state. Its quantum ghost has long since been exorcised by the relentless interrogation of the cosmos. This realization, far from diminishing our wonder, deepens it in ways we are only beginning to grasp. It has also become a profoundly practical piece of knowledge, a key that unlocks new technological frontiers while simultaneously defining their limits. Consider the quest for quantum computing. Here in this extraordinary endeavor, decoherence is not a theoretical curiosity. It is the ultimate adversary. A quantum computer's immense power derives from its ability to hold on to that fragile, ghostly state of superposition. Its qubits, the quantum version of classical bits, must exist as a symphony of both 0 and 1, simultaneously exploring a vast landscape of solutions all at once. This is the violin note in its moment of perfect isolated purity. But the universe is a noisy place. The very act of building a machine to house these delicate states subjects them to a constant barrage of environmental interference. A stray magnetic field, a tiny temperature fluctuation, a single unwanted vibration. Each is a microscopic spy attempting to measure the qubits to learn their secret. And the moment that secret leaks out, the moment the qubits become entangled with the outside world, the symphony collapses into a single discordant noise. The quantum calculation is destroyed. Decoherence is the dragon at the gates of the quantum kingdom. Engineers and physicists are now engaged in a heroic battle against this fundamental process. They build elaborate cryogenic chambers colder than the depths of outer space to quell thermal noise. They construct magnetic shielding and vacuum cells of unimaginable quality, all in an attempt to create a tiny pocket of the universe that is for a few precious microseconds deaf to the interrogations of the environment. They are, in essence, trying to build a perfect cathedral of silence for their quantum symphony. Understanding decoherence has also given them their strategy for victory: quantum error correction. By cleverly entangling data across multiple qubits, they can create systems that are robust, where the environment's questions can be detected and the errors they induce can be reversed before the core computation is lost. We are learning to fight the universe's tendency to create classical reality, holding it at bay just long enough to perform calculations that would take a classical computer longer than the age of the cosmos to complete. The very theory that explains our world is the blueprint for how to briefly escape it, but the reach of decoherence extends far beyond our terrestrial technologies. It stretches back to the very beginning of time, offering a compelling explanation for the structure of everything we see. Look out at the night sky. You see a universe of breathtaking structure galaxies, clustered into filaments and superclusters, separated by vast, empty voids. A cosmic web of unimaginable scale. Where did this intricate architecture come from? Our best models tell us that the universe began in an extraordinarily hot, dense, and almost perfectly uniform state, almost The Heisenberg uncertainty principle guaranteed that even in the primordial plasma of the Big Bang, there were tiny, unavoidable quantum fluctuations, minuscule ripples in the energy of spacetime popping in and out of existence. In their nascent state, these were purely quantum phenomena, a superposition of all possible densities, but the universe was undergoing a period of violent exponential expansion known as inflation. This cosmic blowtorch stretched these microscopic quantum fluctuations to astronomical proportions, and as they grew, they inevitably interacted with the sea of other particles, with the very fabric of spacetime itself. They decohered. The process of environmental entanglement selected a specific classical pattern of density variations from the quantum fog of possibilities. This was chosen from the infinite maybes. Those tiny, randomly selected pockets of slightly higher density became the gravitational seeds around which all future structure would form. They were the almost imperceptible flaws in the cosmic marble from which the grand statues of galaxies and galaxy clusters would eventually be carved by gravity over billions of years. Every galaxy, every star, every planet, every one of us owes our existence to a specific pattern of classical reality that was frozen out of the quantum foam at the dawn of time by the mechanism of decoherence. It is the invisible architect of the cosmos, the process that turned quantum randomness into the grand ordered structure of the heavens. This reconciliation of the quantum and the classical also breathes new life into one of the most staggering ideas ever conceived by the human mind, the many worlds interpretation. Before, the idea of the universe constantly splitting into parallel versions of itself seemed like science fiction, a metaphysical leap with no physical mechanism. Decoherence provides that mechanism. The splitting is no longer a mystical event, it is a physical process of disentanglement. When a quantum system interacts with its environment, the whole combined system particle plus universe evolves together. The branch of the wave function where the cat is alive becomes entangled with a version of the environment, including you that perceives a living cat. Simultaneously, the branch where the cat is dead becomes entangled with a different version of the environment and a different you that perceives a dead cat. These two branches, these two entire universes, can no longer interact or interfere with each other because the information that distinguishes them has been thoroughly smeared across trillions of particles. They have decohered from one another. They have branched. From the perspective of anyone inside one of these branches, it appears as if the wave function has collapsed to a single outcome. But from a God's eye view, the full wave function of the multiverse never collapses at all. It simply evolves, branching endlessly into a vast, intricate tree of possible realities, with each path being perfectly real. Decoherence makes the many worlds view not just a philosophical preference, but a direct physical consequence of quantum mechanics without any additional ad hoc rules. It presents us with a vision of reality that is both terrifying and magnificent, a cosmos of infinite possibility where every quantum choice is explored in some corner of a vastly larger existence. And yet, for all the incredible explanatory power of this theory, for all the profound mysteries it has solved, it does not mark the end of our quest. Instead, it illuminates the path forward, showing us the next set of questions, the next layer of the cosmic onion to peel back. Decoherence masterfully explains times, how times the classical world emerges from the quantum. It is the process, the mechanism, the intricate choreography of information and entanglement. But it does not on its own tell us about the ultimate nature of the dancers. What fundamentally times is times the wave function that it describes? Is it a real physical thing, a sort of stuff that permeates the universe, or is it simply a mathematical tool, a statement about our knowledge, or lack thereof, about the system? This question, the ontology of the quantum state, remains a fertile and fierce battleground for physicists and philosophers. And decoherence, while explaining the transition, does not resolve what is transitioning. Furthermore, while we have successfully removed the conscious observer from the process of collapse, we have not removed the mystery of consciousness itself. We are physical systems, collections of atoms and molecules, subject to the same laws of decoherence as a block of stone or a distant star. Our brains are warm, wet, and complex environments, a nightmare for maintaining quantum coherence. And yet from this classical biological machinery, an inner subjective reality emerges, the feeling of being you, the experience of seeing the color red, the sensation of warmth, the internal narrative of thought. How does this subjective awareness arise from the objective physical interactions governed by these fundamental laws? The puzzle of reality's appearance has been solved, but the puzzle of our experience of it remains the great, unconquered frontier. It may be that understanding decoherence is a crucial first step, a way to properly frame the physics of the brain, but it is not the final answer. The journey does not end here, it broadens. We began in a fractured universe split between two seemingly incompatible sets of rules. We now stand in a unified cosmos, one where the classical world we know and love is seen not as a contradiction of the quantum, but as its grandest and most complex expression. Decoherence is the bridge between these two realms. It is the cosmic translator, the process that takes the weird, ghostly language of probability waves and writes it into the firm, definite prose of existence. It reveals a universe not of isolated objects, but of radical, inescapable interconnectedness. Nothing is truly alone. Every particle carries with it a history of its interactions, a memory of its entanglement with the rest of the universe. You are not separate from the world you observe. The light falling on this screen, the air you are breathing, the faint gravitational pull of a distant star, all are subtly, constantly measuring you, entangling with you, defining your classical reality moment by moment. We are all swimmers in a vast quantum ocean, and the ripples of our existence spread out to touch the farthest shores of space-time. The firm ground beneath our feet is an illusion, a collective agreement, an emergent property of a universe that is constantly whispering to itself. The great questions remain beckoning us forward, but we now ask them from a different place. Not from a place of confusion, but from a place of deeper, more profound wonder at the intricate, self-creating tapestry that is our reality. The quantum ghost has not been banished. It has been recognized for what it truly is, the subtle, foundational hum beneath the symphony of the classical world, the architect of everything we see, and the enduring mystery at the very heart of what it means to be.